Good morning, everyone. We are Group 2, and today we'll be presenting our project for SEMV 3513 Automotive Engineering Design, the conceptual design of a portable, foldable battery electric ATV. Our team consists of 5 members myself, Abdullah Ayubioglu, Lai Winking, Loyi P, Navhin Lingam, and Ahmed Adil. Each of us developed an independent conceptual design for the vehicle, covering different subsystems, which we later combined into one final design. Conventional ATVs run on internal combustion engines. They are heavy, noisy, and dependent on fossil fuels, which limits where they can be used. Battery electric ATVs solve some of that, offering lower emissions and quieter operation. But even electric ATVs today are still too bulky for the average person to transport. You'd usually need a trailer or a large vehicle. That's the gap our project addresses. We set out to design a portable, foldable electric ATV, light enough to carry and small enough to fit in a car boot, while still meeting performance and safety targets within a limited budget. Our conceptual design cover 5 subsystems: suspension, powertrain, structure, braking, and the control interface, each validated within an engineering calculation before being combined into a final design, which we'll walk you through next.
For the project overview, our project objective is to develop a highly portable, lightweight, and affordable eATV. So the application is for short distance recreational and utility off-road use. So our key feature for this product is it's designed to fold and fit into a standard passenger cupboard. And our problem statement is conventional ICE ATVs are heavy, noisy, and produce harmful emissions. And existing commercial battery electric ATVs are too heavy and bulky for transport, and our users need cleaner, quieter off-road alternative that does not require specialized transport equipment. For the process, our core design requirement are for the performance, a maximum speed of 30 kilometers per hour, an estimated operating range of 8 to 12 kilometers. A load capacity is for one rider up to 105 kilograms. Our total project budget is 1000 to 1500 ringgit, and our safety requirements are effective braking, stable steering, and reliable structural strength. So the way we designed this product is we first identified the needs using the HRQ, and then we translated them into a measurable project product design specification. Then each one of us had a concept generation. We we generated multiple concepts across 5 critical subsystems. Then from those systems, we done engineering validation where we executed calculations for load, suspension stiffness, motor power, gearing, and braking torque. And then for the structure, we did structural verification using finite element analysis to evaluate chassis stress, displacement, and factor of safety.
For our literature review, we studied the main working systems of a battery electric all-terrain vehicle or EATV. Compared with conventional petrol-powered ATVs, EATVs produce less noise, lower emissions, and provide better energy efficiency. However, many existing EATVs are still heavy, bulky, and difficult to transport. From the literature, we identified 5 main systems: the energy storage systems, power electronics, electric motor, drivetrain, and vehicle control system. The battery stores electrical energy, while the battery management system protects it. The controller and inverter regulate the power supply to the motor. The electric motor then produces torque, and then the drivetrain transfers these torques to the wheels. We also reviewed regenerative braking and thermal management, which can improve efficiency, safety, and component life. Now, overall, the energy flow is from the battery through the controller and motor, the drivetrain and wheels. These findings guided the development of our low-cost and portable EATV design.
For sustainability, we assess the design across three dimensions. Environmentally, the eATV produces zero tailpipe emissions and runs quieter than a petrol ATV, and the mild steel frame is recyclable and repairable by welding, while PVC is limited to non-structural covers that can be replaced without discarding the whole frame. Economically, we used locally available Malaysian components and standard fasteners, and made the battery, motor and controller modular so repairs stay low cost. Socially, it's a low noise option suited for parks, farms and campuses with safety enforced through a kill switch, guarded chains and rotors, and mandatory helmet and PPE use. Beyond that, we applied a 6R framework to guide our design choices: reduce through the open frame and minimal panels, reuse with the inspected donor parts, repair and refurbish through the bolted covers and removable components, and recycle and recover using recyclable steel and proper battery recycling at end of life. Overall, the design aligns with 4 UN Sustainable Development Goals: clean energy, industry innovation, responsible consumption, and climate action.
Lai Wenqing, and I will present the Part 5 Final Design and Detail Analysis. This slide shows our final ATV design after evaluating different concept and engineering requirements. On the left is the detailed sketch and 3D model of our portable electric ATV. The final design used an open frame portable structure, which makes the vehicle lightweight, portable, and easy to manufacture while still maintaining good structural strength. On the right side is the final design specification. Our final design used a 750 watt BLDC motor, 36-volt 15 ampere hour lithium-ion battery, hydraulic disc brake, and coil spring suspension. The ATV weighs 35 kg, but it can carry a 105 kg design load, reach a maximum speed of 30 km per hour, and meets our final target cost of 1,000 to 1,500 ringgit. At the bottom, the structural simulation result shows that the chassis performs safely under the design load. The maximum stress is 82.4 megapascal, the maximum displacement is only 2.18 millimeter, and the safety factor is 3.03, which confirms that the design is safe and reliable. Next, moving on to Part 6 result and discussions. Based on our result, the ATV successfully achieved the project objective. It meets the target for weight, speed, safety, and portable and cost. The main strength of the design are its lightweight and portable structure, good structural strength, low manufacturing cost, and easy to manufacture. For the future improvements, we recommend that adding waterproof protection, reinforcing the folding hinge, and performing fanning weight and dynamic analysis to further improve durability. Overall, the proposed electric ATV successfully meets the product design specification (PDS) and provide a good balance between the performance, safety, portability, manufacturability, and cost. We believe that this design is practical, safe, and suitable for lightweight off-road recreational use. Thank you.